Okay, thanks. So yeah, this is very much a work in progress, and it's some work that started before GSWA got involved, but thanks to them for supporting a part of this work. And as anybody that was growing up in the 70s, as I was, there was a great deal of excitement then about being able to turn donuts into coffee cups. And that, for me, was my first introduction to topology, and I'm not sure I know all that much more now. So what I'm going to be doing, start off, I'll talk about what I mean about the topology of geology, what it means to me. And I'm going to talk about some 2D cases, how we can use some of that knowledge to go into 3D, and how, in fact, understanding 3D topology can help us with the geological uncertainty that we're working with in our 3D models. So I should just point out that Vitaly couldn't be here today because he had a prior engagement. Well, in fact, he was engaged, now he's married. So Vitaly will be back in a couple of weeks, and he's done a lot of the coding on this. The other person that I should point out that's done a lot of work on this is Sam Tielli, who was a master's student here, who's now gone to Monash University to do his PhD on a completely different topic. But he's got 2 papers that are going to be coming out of his master's project in the next couple of months. So I'm going to start off talking about mineral systems a bit. Well, not really in very much detail. I'm sure you've all seen the departed Cam McCaig give talks on this topic with John Hronsky, who's still here. Talking about these sorts of diagrams, talking about fluid flow and fluid reservoirs and fluid sinks and entropy and energy sources. And I thought it might be fun, just before he left, to take this paper that was in a special volume of Economic Geology and put it into a word cloud. And you can see that deposits figures quite heavily in this, and systems. And if you remove the sort of obvious words like ore deposits, what you're left with is a lot of statements that are about energy and fluids and magma, so mass, transferring via flow, flux, with barriers and focused material in some sort of organized way. And what this is really telling us in a mineral system is that the relationships between things in a mineral system are important. We need to get mass and energy from point A to point B, and at some stage we have to stop it getting to point C. So a lot of what we're looking at is the spatial and temporal relationships between different aspects of geology. And that's really what we mean by topology. So we need to understand, as geologists and explorers, spatial and temporal relationships. Well, that's not new. So we need to understand fluid pathways and barriers. We need to understand overprinting relationships. We need to understand neighborhood relationships. And we know all this, and that's the way this is used at the moment, at least in one aspect of this work, is to capture this sort of information, these sort of relationships, in prospectivity mapping as things like proximity buffers. So this is an area that I've spent a fair bit of time trekking across recently. It's the Kumasi Basin in Ghana, and there was a paper that came out this year in Ore Geology Reviews doing a prospectivity analysis of this basin. And I'm not going to go into all the details, and I'm not picking on this paper as being good or bad or anything. It's just that this is a fairly standard approach where we have a map of the geology, and it's a very simplified map, and this is essentially a flysch basin, and it's been divided up into 4 rock types. In fact, the things that are labeled Mesozoic are Proterozoic, but that doesn't matter because they're just dikes and things, so not a problem. We have a whole series of different structures, and from all of this and from other layers of information, evidence information, they've made a prospectivity map looking for orogenic gold that picks out some of the areas which are known to be prospective for gold already. And one of the problems, of course, with this type of analysis is that there's an awful lot of faults in this area and here, but there's an awful lot of faults in this area here because there's already quite a lot of gold known from that area, so there's a lot more mapping done in that area. There's a much higher resolution geophysics in that area. So the fact that this is a detailed area is partly because there are more faults, but it's also partly because there's more mapping. So this is how we can combine the information, but there are other ways as well, and that's what we're going to look at now. So when I'm talking about topology, I'm talking about spatial and temporal relationships. So that's, all of that together for me is the topology of geology. And there's been a fair amount of work on spatial relationships, and this doesn't look much like geology, although it looks a bit like Jeremy's first model. But there's all sorts of different ways that you can analyze the relationship between two polygonal areas, and they can not meet at all. They can meet, they can overlap, they can be the same. One can be inside the other, one can be partially covered by the other, and so on and so forth. And Eggenhofer came up with a complete set of these relationships, and in 3D it obviously gets more complicated. And most of the time you think, well, most of my geology actually looks like this. I have rock type A, and then I've got rock type B, and they're next to each other. But when you think about it, things like structural overprints and alteration overprints, in fact, lead to many of these other types of relationships. For the rest of this talk, I'm mostly going to be talking about these sorts of relationships because you've got to start somewhere simple. But that's not to say that these other ones don't have geological relevance as well. Just as you have spatial relationships, you also have temporal relationships. And so we've tried to color code them in the same way that you can have some rock type or some structure which is clearly younger than another one or older than another one. You can have two types that one precedes another one immediately, that they overlap, or that we just don't know. And so these are, in a sense, directly equivalent topological relationships in time as we had in space. And obviously, in geology, we want to be looking at both of these at the same time. And about 40 years ago, or slightly more than 40 years ago now, a CSIRO scientist called Carrie Burns basically worked all of this out. So we can stop here. He's published 5 or 6 papers on this stuff. And this is an example of the 1975 paper where he's got a, obviously, synthetic geological map with a whole series of different age relationships that are obvious to geologists. And he's coded those relationships in a simplified map form where the arrows are pointing to different features in terms of their age. So the arrows are pointing, in this case, to the younger units in all of these relationships, and he converted this map view into a time network where you can follow the age relationships of all of these units, and sometimes there was an ambiguity, so you had a fork and then it came back together again. So he came up with network diagrams, and he also came up with what we now call adjacency matrices. So you can plot all of these relationships between A to L and A to L as age relationships based on the geology map. And he published, Carrie Burns published 5 or 6 papers on this topic and then got bored and did something else. And I think one of the reasons, I don't know the person at all, he's still working, but he's in the States now, works on something completely different. But I suspect one of the reasons that he got bored and went home was that in 1975, that was 7 years before ArcGIS version 1 was published. So there was really no mathematical, sensible, or software basis, either in terms of the data structures for putting geology into computers, or the logical software framework to actually do this automatically. So he could draw it, and he thought of just about everything in 1975, but he couldn't do anything about it because there were no GISs. All geology maps were still being hand-drawn. If they were being done on computers, which I think in 75 they weren't, but if they were being done using computers, it was essentially as a drawing exercise, not with any sort of real capturing of spatial information. So when I started to think about this Of course, it's always exciting to find somebody else has done all of this before, and it's disappointing, but it's clear that he reached a point where basically technology wasn't up to it. And fortunately today, technology is up to it, so now we can pick up where he left off 40 years ago. So the work that we've been doing is looking at, and these are network diagrams, looking at topological relationships in 2D. And if you can do exactly the same thing in 3D, there's no real problem. And if we take a simple layer cake stratigraphy, we can see that the topology is very simple. Each node, which is these circles, represents one unit in the geology, and the edges or arcs, different people call them different things, join up the nodes to show some sort of spatial relationship. And here the gray lines means that it's a stratigraphic relationship, and you end up with a very simple description of a map. If you have an unconformity, you end up with something that looks a bit like a Hill's hoist, and all of these green lines are showing unconformable contacts. You can do the same with igneous contacts, and you get what Sam liked to call the angel patterns. And you also, if you have a fault, which is in red, you get this sort of staircase pattern. So these different structures are demonstrating different types of topological relationships, which when you look at them, you can interpret back in terms of geological relationships. You can also get more complicated, but for the moment, we're going to leave it at these sort of simple representations. So we have this idea that we have spatial relationships and a spatial topology. We have temporal relationships, so time relationships, and together they are implying, or we can interpret them in terms of process models, in terms of truncation, intrusions, erosions, deposition, stratigraphic relationships. So that's the type of analysis that I'm going to be talking about now, and then I'm going to show some examples. And I said I'm going to tell you what I'm not talking about. Topology, unfortunately, just like donuts and coffee cups, is used in many different ways. And I'm not talking about map topology in the way that I'm trying to tidy up a map to get rid of bits that are left over. And I'm not trying to avoid the fact that I've got polygons overlapping when I'm making my geology map. That's also called topology, and quite correctly called topology, but I'm not going to talk about that. And I'm not going to talk about it in 3D to try and make nicer meshes. And some people spend a lot of time trying to make better meshes for their 3D models, and it's very important because these meshes are often the basis of doing process modeling, so fluid flow modeling, all those sorts of things. So it is important to do this sort of mesh topology. It's an endless black hole, but that's a different problem, but it's not what I'm going to be talking about when I talk about topology. So we've got these sort of network diagrams, and these, even in 2D and even with a quite simple structure where we have a faulted system that's cut by a dike, we can see that the topology becomes quite complicated quite quickly. So another way of looking at this is to simplify it and say, well, let's just look at the structural domains. And we can do a topological analysis of the structural domains. So everything that's contiguous that's below this fault and to the left of this dike, we just consider that as a single domain. And that's a way of simplifying what we're looking at. These adjacency matrices that we were already introduced 40 years ago in geology, we can use them again to remove the complexity of the topological relationships and just put it down into a simple matrix form, so that for every lithology here, we can compare whether it contacts with another lithology, and we can compare what type of contacts it have. So it can be faulted, stratigraphic, intrusive, or no contacts at all. So it's a summary diagram that tells us for any given map area what we might expect to see in terms of, does rock A touch rock B? If so, why? And of course, sometimes you have the possibility that rock A touches rock B for two different reasons. Some places it's faulted and some places it's a stratigraphic contact. You can have lots more fun. There's lots of ways of people trying to analyze topology. This is something called a hive diagram, where they've got different axes, stratigraphic age, structural age, surface area. And at this point, you start to think, well, maybe my map wasn't that complicated after all, and maybe I'll stick to the maps. But what's important about this is that this is a mathematical description of your map that you can compare with something else, whereas comparing two maps is actually very difficult. So in a world where we suddenly have not one geology model, but thousands, this is a possible route to comparing our different geological models. But let's start off in 2D first of all, and let's go to the Mount Bruce area up north in WA, and we've got a nice map, and we can see, you know, structural geologists are happy because you can see some nice folds, you can see some refolded basin and dome structures, you can see all sorts of different things going on here. But because it's been folded and because it has a fairly interesting structural history, you sometimes find it more difficult to pick out some of the simpler essences of this area. And in the particular, what we're looking at the moment with GSWA is developing ways of analyzing the stratigraphic relationships in a map which has already been multiply deformed and where those relationships are no longer quite as obvious as they might have been. And so these are all just a simple alphabetically sorted list of all the different formations in this map sheet. It's taken from the 1 to 500,000 geology layer, so it's just essentially a shapefile. And there are many different ways of looking at these stratigraphic relationships. We've got the old map sheet, which had this stratigraphic legend here, and if we take the Duck Creek dolomite just at random, we can see where it is in the stratigraphy that was applied to this whole map sheet, so the Mount Bruce map sheet. We have the modern equivalent, which is for the geological map of Western Australia, looking at these stratigraphic relationships with some sort of absolute time information and relationship with other types of units. And we also have the GSWA explanatory note system, which is a new database that allows you to query this database for information about any specific formation in Western Australia. And there are different ways of understanding the relationships between different units in this stratigraphy. The old map sheets used to come with explanatory notices in the form of paper, and they've now all been digitized, and you can download them as PDFs. And these are just a couple of examples from this same map sheet describing the relationships between a particular unit and its neighboring units. And that's the sort of information that's being transferred over or updated in the explanatory notes. Obviously, these have a potential for data mining, and for that, you've got a CEJ. So when we look at the shapefile that we use for that map, it's got a number of different types of information, in which I'm showing 4 here. It's got the formation name or the unit name, which group that unit belongs to, what the maximum and minimum ages are, but you'll see that within a single group, often there's no distinction available for that information. And again, that's just the list of things there. So what we can do is we can take the map as a shapefile and not just treat it as a map, but treat it as a series of polygons where we can do spatial queries on the relationships between each polygon and its neighbors. And we can do it on the relationships between the polygons and the faults as well, and we'll see why we have to do that. So this is just the example of a faulted unconformity that we have here. We can see the unconformity there. We can see the fault coming through there. This is obviously a synthetic example. We take what we do is we take our shape files and we convert them into something called WKT format. It's just an ASCII format that makes it easier for us to faff with later on. And so this is a little bit of that Mount Bruce map. We can see the big black lines that are faults, and we can see the different units. And what Vitaly Ogako has been able to do is to extract the topological information directly from these shapefiles. So essentially, the inputs for this are the geology polygons and the faults. Because you need the faults because you need to be able to say what is, for any given segment of this contact, is this a fault geology contact or is this a geology contact? Is it a contact that's defined by the fact that there's a fault separating two lithologies, or is it in fact just a stratigraphic contact? So we have those relationships here, we can extract them, and with that we can then produce an analysis that says, you know, this purple against blue, well, because it's coincident with a fault, therefore I know it's a fault contact. Whereas this purple against blue here is a stratigraphic contact because there's no faults mapped. This, of course, depends on the map being right, but of course the map's right, it's GSWA. Now, don't look like that. So this is what we get out of it. So we press the button and the code runs for a second or two, and we get a topology of the stratigraphical relationships. Don't worry about the colors of the lines here. The thickness of the lines is proportional to how much contact length there is between the different units. So we can see we've got arrows. So arrows are saying A is younger than B, and if the arrows go in both directions, it means that that table information on max and min ages was ambiguous in terms of age relationships. And we've also got the rectangles which surround formations which are in a single group. So we can see that there's a complicated overall relationships, but often within a single group there isn't too much complexity. And if we just pick a couple of examples of what this can tell us about the stratigraphic relationships, so we pick out these two units here and look at what their stratigraphic relationships are based on the map analysis, we can look at things like this. So this is the Hardy Formation, and the Hardy Formation sits on top stratigraphically of a whole series of different units, and that matches exactly what we see in the old explanatory note that goes for the Hardy Formation, is that it's unconformably overlies all of these different units as already described. And you can interpret that as being some sort of offlap relationship based on the topological relationships we see here, based on the stratigraphy, the fact that it's sitting stratigraphically over all of these different units. And it's that unit here, this sort of pale green unit that we're looking at. The other example is the Kungra Formation, this sort of pinky purpley color here. And here we have a whole series of units that are sitting on top of it. And that would be some sort of more on-lap relationship. So based on purely on the geology map, and this is sort of throwing away the structural information apart from the faults, we're able to extract stratigraphic information in terms of relationships directly from the map. And then we can use it to compare, and in this case, when we compare it with the explanatory note, it doesn't really talk about that sort of relationship in the note. That's not to say the geologists didn't see it, but they haven't written it down. So that means that information hasn't been captured within that note. So there are two ways you can look at that. One is that some of these contacts lines are quite thin, so they might not be all that important, or that the relationships in the field weren't that obvious, but it's only when you look at the whole map that it comes out. The other thing that's interesting about, to me at least, about this sort of analysis is that you can do it at multiple scales. You can do it at the scale of individual formations, but you can also do it at the group scale. So you can go up scale in terms of the geological classifications from the formation scale in these sort of analyses to the full group scale topology of that map sheet there. But there's another way of changing scales as well, and that's to say, well, here we're going to take it for the whole map, what these relationships are, and here we're going to take it just for this polygon. So we can get a local relationship, what this polygon sees relative to the rest of the world. And if you bring that back to the sort of prospectivity analysis and a mineral systems analysis of pathways, we're now able to go from something where we're giving a global analysis of the stratigraphy of this map sheet or of Western Australia to having local stratigraphic relationships and local pathways and local relationships. So this is the local relationship of that polygon where it only actually sees two rock types or two formations, even though on the scale of that map it sees a whole series of different things. And we can also divide it up in terms of scale in another way and just divide the map stupidly into quarters. And these are the different topologies that we get for those different quarters of the map sheet. So we get the idea that we can look at how the stratigraphy of this area changes as we zoom in or out or as we move across the area. And one of the things which is a wild assertion that I haven't tested is that we might be able to do this sort of analysis over large basins to find out where the subbasins are, to see where there are sharp changes in topology. It may work, it might not work, but to me there's a potential for that at least. When we put in the fault network, which is this layer here for that area, we get another type of information. Up till now we've thrown away the faults because we wanted to look at the stratigraphy. But if you want to look at the faults and the stratigraphy at the same time, it makes a horribly complicated diagram like that, which I've zoomed in here, and now we can see what those colored lines mean. The dark blue lines are purely stratigraphic relationships. The dark red lines are purely fault contacts, and the green lines are some sort of mixture in between. So now we can see that there's some units which are heavily modified by the faults, and we can see that because there's a whole series of connections between this Bungina formation, which we follow up, which go to a whole series of other formations. So now we're saying that all of these formations up here are connected to this formation by faults. So now we can start to think about fluid pathways. We can start to say that there is a plumbing system, which is what I say here, is that when we add the fault contacts, this diagram represents some of the key topological aspects of a mineral system, because we're looking at the relationships between, spatial relationships between lithological units and the fault connectivity between those same units on any given scale that we choose, on the scale of one single polygon or the entire map sheet of Western Australia or any sub-region that we care to look at. I don't know quite how we're going to use this yet, but that's exactly what we're going to find out in the next year or two. Of course, that's all in 2D, and to be honest, one of the reasons for doing this in the first place was to see how much information we could extract from a map in order to generate 3D models, which is what I'm actually supposed to be working on. And so, the traditional way of making 3D models is to collect all your data, and hopefully it's not on paper anymore, but to collect all your data sets and to put them into a 3D modeling software and to produce a model of in this case, the Ashanti Belt in southwest Ghana. But because all of these data sets are in fact now digital, and because we are getting better at analyzing those digital data sets in terms of geological meaning, there is the potential to imagine a world where these sort of 3D models are available on demand. So instead of having to ask somebody to go and make you a 3D model, that all of those online GSWA databases might provide enough information to make the 3D model without you having to do it very much at all. And so that's another thing, another area of where topology comes in. And if we think about what we need to make a 3D geological model, and I'm going to use the example of GeoModeler because it's the one that we play with the most as a research program, we need to know what the topography of an area is. We need to know what the stratigraphic contacts, where they are, what their geometry is, with structural orientation information, so what's the dip of this contact. We need to know where the faults are, and we need to know what their dips and orientations are. We need to know stratigraphy. We need to know fault age relationships, and we need to know fault stratigraphy age relationships. And if we go through that, well, topography's a given. We can get that anywhere now at high enough resolution. We know from the topological analysis we can extract the stratigraphic contacts from our geology map, and we can combine it with the Works database to get structural information where available. We can get faults from the maps, and we can combine it with Works. There's very little deep information on faults in the map databases or in Works, but whatever there is, we can use it. We could imagine using three-point analysis in more rugged topography to get that information. Stratigraphy, we've shown that we're starting to have the ability to extract stratigraphic information directly from the map without actually having to have a predefined legend for any given region. The fault-age relationships is a problem, but we can use simple relationships of truncation and the orientations of structures, hopefully, to help us. But again, it becomes a map analytic problem. And the fault stratigraphy age relationships we're already extracting from those geology maps. So the idea is that we might be able to draw a rectangle around a box of Western Australia, and using the geology maps, and sometimes there's sections we can use, the Works database for structural information, map analytics to extract the stratigraphic information to produce a 3D model. And you'll notice here I don't provide the answer because we haven't done it yet. But that's something that we're following up. But of course, the obvious question there is what happens when you don't have enough information? And we never will have enough information, let's face it. If you look at the map of faults for that sheet, there is no structural information that tells you what the dip of the faults are. And there are a couple of different ways we can go with that. These symbols here, some of them happen to be parallel to the faults, so maybe you could say, well, maybe there's a relationship there, but there doesn't have to be, because it's clearly not a structural observation of a fault dip, it's a bed dip. A couple of different ways we can go with that. Fortunately, our group as a whole for several years now has been looking at Monte Carlo simulations with multiple hypotheses, and Jeremy was using that just before. So the idea is that if we don't know what the dip of the fault is, we can simulate 15 different models or 100 different models with different dips and see where that gets us. So we're not restricted to the idea that not having enough information, it's the nonsense filters just triggered. Just the idea that if we don't have enough information, that means we can't make a model. Because we're going down a Monte Carlo simulation route, we can simulate lots of different models, assuming that we don't have enough data. So we can have this idea of trying out different fault dips and resulting with a whole range of different models as possible solutions to the 3D problem. So even though, of course, we will never have enough data to automatically produce our 3D model, we have the possibility to say what is possible in 3D beneath the surface. And as you've seen, Jeremy is able to take that uncertainty in geology and turn it into predictions of what the three-dimensional geology is as well. And this example is 2D, but of course the same logic applies in 3D. So we can bring in the geophysics as a possible constraint on improving our three-dimensional models, even if we don't have sufficient data from the geology itself. And that's obviously what geophysics is good at. The other aspect of 3D uncertainty and producing these Monte Carlo simulations, and this isn't going to go too much longer, fortunately, is that we can go from a 3D geological model to its topological description, and this is a network diagram for this model. And one of the important things about this topology, apart from the fact that it's telling us about the relationships of the different units in the area, is that we're going, even from a simple system like that, we're going from 1/3 of a million voxels here to 82 different elements here. So it's a massive reduction in dimensionality. And if we want to compare different models, it might be better to compare the topology of the models than to compare the models themselves. And if we've generated 1,000 models, 1,000 times that makes a very big number. 1,000 times that makes 82,000. So there's distinct advantages if we can convince ourselves that this is retaining the essence of the model, and in a mineral system sense it might well be, because it's retaining the relationships, the fault relationships and the stratigraphic relationships. So the massive reduction in dimensionality could be an important help for us. And this is in fact the work that Sam Thiele was doing in his master's, was looking at topological uncertainty in 3D models. And one of the examples he used was a model that was built a few years ago by Robin Armitt from Monash University of the Mount Painter Inlier in South Australia. And this is a cutaway view of that model, and there's the geological history. And this one has 50 million voxels. And to be honest, I can't remember how many topological elements it had, but it's orders of magnitude less than that anyway, several orders of magnitude. And what he did, one of the reasons that it's useful to look at the topology is because you can compare all of the topologies very quickly. It's a very fast calculation. And the way that you can compare them is by using this Jacquard coefficient, which essentially looks at in terms of the topological relationships, the ratio between the intersection of the different topological models and their union. And that's, you can just use as a characteristic of how similar these different models are in terms of their topology. And what you can use then is you can use that to say, well, as I generate more and more different Monte Carlo models, am I getting a plateau in the number of unique or distinct topologies that I produce, or is it continuing to climb up towards infinity? And if you're here, it tells you that you probably haven't sampled the model space enough. And if you're getting something like this, then you're getting closer to sampling the model space. So as an overall analysis, it's telling us that this is where you want to be, not here. The other aspect that you can use is you can look at the topological variability, and I'm not going to go into this in detail, and you'll be able to read about it fairly soon, is for all the different structural features in the model, he can see which features resulted in the most uncertainty in the topology. So essentially, the uncertainty in the topology was dominated by two particular faults. And that's interesting because it tells you where you need to collect more data to better constrain the variability in the model. We can identify that these two particular faults were dominating the uncertainty in the model. And the next slide goes back to the question I asked Jeremy, is that in fact we can classify in terms of the topology all of the models, and he made 1,000 models or several hundred, I forget the exact number. We can classify them according to their topology into different classes, and looking at them geologically is very hard, and it's something that's just a limit of our ability to compare 3D geological models. But we can automatically analyze their topology to come up with 8 different classes, which first order don't all look all that different, but the topological analysis demonstrated they were different, and they could be the starting point for Jeremy's inversions. So I'm going to wrap it up there because we're already 5 minutes past 0 o'clock. So the conclusions are that spatial and temporal topology have the potential to provide essential, interesting insights into mineral systems, that we can extract, we already have the ability to extract this topology from 2D maps and from 3D models. And we can view the extracted topology in terms of local and regional variations in stratigraphic relationships, but also in terms of relationships between faults and different stratigraphic units, which are key mineral system components. There's a potential to use this stratigraphic analysis together with the fault analysis to automate or to semi-automate the 2D map to 3D model transformation. And that when we're building 3D models, when we take into account the topology, it's an interesting characteristic that we can use to better understand the variations in the models that we're building. Thank you.